Okay, good morning everyone. Let's start. So we'll revisit something that we did near the end of the last lecture, and that was to ask how the Schrödinger equation is proposed. I've emphasized many times it is a proposal, and that's essentially why it's named after him. It's not derivable from something, because this is a new kind of physics, quantum physics, and we needed some concepts and some equations which would allow us to calculate those concepts. So the key concept in quantum physics turns out to be wave function psi of x and t, and this is supposed to be a parallel to the description of a classical wave, which we did in some detail. So we discussed that in a classical wave there is a function alpha of x and t which describes the wave. We showed that if you want such a function to have a definite wave number, then the function in space is e to the I k dot x, but you can take linear combinations of it which no longer have a definite wave number, but they can be localized. That was one thing we discussed. And the most general alpha of x is some linear combination. Again, I'm going to use 1D notation. And this is to be understood as a linear combination of plane waves. And plane waves is just e to the I kx. It's just the name for e to the I kx. If you look at those waves in 3 dimensions, they are e to the I k dot x, and then they have a plane front. So they are plane fronted waves, that's why they are called plane waves. Okay, so far so good. And just this much information, along with the fact that E equals T plus V, where this is kinetic and this is potential energy for a particle that we want to describe. What we say is, well, we want the statement that the kinetic plus potential energy of the particle is equal to its total energy, and we want to implement that requirement on the wave function of a particle. So we need an equation which says that E times the wave function psi of x is equal to p squared by 2m plus v of x on psi of x. Now psi of x in classical physics plays no role. The equation is just E equals this plus this. But now we want the wave function to satisfy a condition, and we know that on the wave function psi of x we can't just multiply by the number p, because p is the momentum. It's analogous to the wave vector, and that exists only in the wave vector or momentum basis. But here we are looking at functions of x, and we know that on such functions p goes to minus I h bar gradient in x. So therefore we say that this function satisfies that the differential operator minus h bar squared by 2m gradient squared plus v of x on psi of x, this should be equal to E times psi of x. And this is the time independent Schrödinger equation, and it's the first equation he wrote down. TISE stands for time independent Schrödinger equation. We'll use this terminology quite often. Good. Okay. So again, it's neither more nor less than a proposal, and it's a very intriguing one to which I'll come back in a few minutes. But we have a problem, which is that this is how a time independent wave function behaves, and we still don't know how a time-dependent wave function behaves. But actually, solutions of this equation must have an obvious time dependence for the reason that the plane wave, so we go back to classical waves, and we remember that the plane wave e to the I kx in time when we want to look at the time dependence is replaced by this. Okay, this is the plane wave only at a fixed time. The plane wave as a function of x and t is that. Maybe I'll be careful and put the vector signs now. But there are no vector signs on omega and t, those are just numbers. And this is angular frequency. So this is a plane wave of definite wave vector and definite angular frequency. And again, we are free to superpose it and get plane waves which have a sum over wave numbers as well as a sum over angular frequencies. That's up to us. We can always take linear combinations of plane waves. Okay. But remember that E is equal to h bar omega is another way to restate Planck's law. That in the quantum theory, the energy is proportional to this angular frequency, this thing here. And therefore, it means that a wave function of definite energy is this is equal to the wave function independent of time times this quantity. We simply replace omega here by E upon h bar using this box relation. Okay. Now that doesn't affect the time independent Schrödinger equation, because if I just put in here e to the minus I e by h bar t, then I can just put it on both sides. Okay, I can just put this factor everywhere. Because this differential operator differentiates only in x, it doesn't care about t. So that's just an overall factor. But the point is that all these statements are true of wave functions of definite energy, and Schrödinger noted that there could be wave functions which don't have definite energy. And there are actually two interesting ways in which a wave function might not have definite energy, and let's see them. So one way that it can happen is that we superpose more than one, or we superpose wave functions of different energy. In the particle picture, it's difficult to know what this means, because a particle, as we know it, has a fixed energy. But this is a wave function, and we know for sure that waves can be superposed. Superposition principle is one of the fundamental principles of waves. So we are free to add waves of different energies, and it's our problem to figure out what that means for the particle. And we'll spend this lecture and the next lecture and the next week also discussing exactly these questions. So this is one way that we get a wave function which doesn't have a definite energy. It could be a superposition of wave functions, each of which has a definite energy, E1, E2, E3, but in the sum, that energy is not definite. Okay? There's a second way, which is, we talked about this potential. What if this potential in which the particle is moving is time dependent? Do you know what happens if a particle moves in a time dependent potential? What happens to its energy? Decreases. I don't know. I mean, why can't it increase? Can't I go behind the particle and keep pushing it? Isn't that a time-dependent potential? Yes.
The total energy is not constant.
Very good. The total energy is not constant, or total energy is not conserved. Okay? Now before you start worrying what this means, of course the total energy of the system is conserved because that potential which depends on time is doing some work. It could be, for example, a driven oscillator. I suppose you did this problem last year. Or it could be a damping for, it could be something that oscillates, some sinusoidal oscillation. In fact, potentials that particles move in are more often time dependent than not. Assuming time independent is a very abstract thing that is only appropriate in limited situations. Okay, so given that in this situation the energy is not conserved, so we don't expect a wave function of definite energy, so our wave function will not have definite energy. And Schrödinger asked himself and then wrote it down, what shall we do in such situations, any such situations where the wave function doesn't have definite energy. And he went back to this equation and he said, look, there's a nice manipulation I can do, which is to take the left side of this equation and rewrite it as I h bar d by dt of psi of x and t, where psi of x and t is psi of x times this phase factor. D by dt does not care about psi. When it acts on this factor, it pulls out minus e upon h bar, but we have plus I h bar here. Those two things cancel and I am left with e. So this is the same as this for wave functions of definite energy. But the nice thing is that now this equation, which I just rewrite like this, doesn't have any energy appearing in it. It has a potential, which is a contribution to the energy. It has a kinetic term, but it doesn't have any total energy. It just says that the sum of these things acting on the wave function is the time derivative of the wave function. And he said, well, this is certainly true when the wave function has definite energy. We just rewrote the time independent equation in this way. Okay? But he said, if it's true in that special occasion, let's assume that it's true in general. So that's the next postulate of Schrödinger. And this is called the time dependent Schrödinger equation. And it says that to determine a wave function, I should match I h bar d by dt of the wave function with that right hand side, which looks formally like an energy operator. It's an operator because this is a derivative which is going to act. Operator acts on a function, gives me another function. Okay, and in fact this goes by the name Hamiltonian, but and sometimes it's called H. And then the result is that I h bar d by dt of psi is H acting on psi, capital H acting on psi. So that's a short way of writing the equation. So are there any questions about this? Yes. It can be a function of t now. We'll allow it. Yes.
Why he didn't do double derivative of I?
Because single derivative gives me e. This is a from here to here for the fixed energy case. It's straightforward, right? One derivative of this brings out e. So d by dt of psi for this kind of psi is e times psi up to these factors. Okay? So he had no choice, it wasn't a choice. However, those of you who know special relativity will wonder because this equation treats time and space on a different footing. Space has a double derivative, time has a single derivative, and there's no chance that this can be invariant under the equations of special relativity, and it's not. So it's a non-relativistic equation. And the Schrödinger equation is always non-relativistic. There is, as far as I know, there is no relativistic Schrödinger equation. In fact, I actually this weekend I read his paper again. He comments towards the end that, you know, this is all fine. We'll see the consequences of this equation for non-relativistic particles, where there are lots of experiments to do. But what if the situation was relativistic? This equation would not work. Somebody should find an equation that does work. Okay, and a few years later, Dirac did that, and that's the Dirac equation. But that's an advanced topic in quantum physics, and this course is Introductory Quantum Physics. Yes.
Writing that to be the Hamiltonian generalizes it a lot more, right? Because Hamiltonian is not always T plus V.
The Hamiltonian, yeah, good point. The Hamiltonian is not always T plus V, so in that sense, calling this the Hamiltonian is, yeah, indeed. So now the question arises, we are again in this course, we'll largely deal with Hamiltonians of this form. But there are many systems, and notably including a motion of a particle in a magnetic field, which is a very, very common system, where Hamiltonian is not simply T plus V. You require a little bit, a few more gadgets to write it. And the assumption then is that since this is true in the simple system, we'll generalize it by allowing this to always be the Hamiltonian. One advantage is that the Hamiltonian is an object in classical physics, and classical physics was well understood by all these people. So they are like, if from classical physics, if you give me a Hamiltonian and ask me to understand the corresponding quantum problem, I'll just put it into this equation. So indeed, as you correctly point out, there are steps of generalization. And at each such step, you should be alert that you are not making some mistake. You might generalize in a way that gives you nonsensical answers, but actually it's done extremely well. And where it breaks down is really in the domain of relativity. And then a lot of things happen once you get to relativistic equations, which are all, for those interested, will be subjects of your future study. But for us, this equation will give us plenty to do. Yes?
I didn't understand why not having a definite energy causes a problem.
Causes a problem because the time-independent Schrödinger equation says E times psi is this thing times psi. So what is E if the wave function doesn't have a definite energy? What should I put in place of E? If the wave function is a sum of two wave functions with energies E1 and E2, what should I put here in this equation?
Like we can't directly add the sum of the.
Put E1 plus E2 here?
Yeah.
No, that doesn't make sense. First of all, the sum of two wave functions of energy E1 and E2 is different from the wave function of energy E1 plus E2. And you can immediately see that if you focus your attention on this factor. If I take this factor for E1 and this factor for E2 and add them, do I get this factor for E1 plus E2? No. That's the reason. Yes?
So what exactly is conserved in the system time varying potential?
Maybe nothing, depending on the system. Not that every system conserves things. We know plenty of systems that don't conserve energy. Now, of course, again, it is not that the energy is not conserved if I look at everything, system and environment. So the energy will go somewhere. Even if there's friction which slows down, you press brakes and your car slows down or your bike slows down, your energy is certainly not conserved, but that is going to cause some heat energy and all that. And if you take your whole thing in a box and count the total energy, it's always conserved. It's a principle of physics.
So for that system, the energy is not conserved.
Sorry?
If you just look at the
If you just look at the system, the energy is not conserved. Yes.
So, but is it
Yes.
possible that I have a perfectly insulated and a perfect system, complete vacuum?
Yeah.
If there is no means of transfer of energy to outer environment, then is there a possibility of potential being varied, or it would always be the same?
Yeah. So if I have a completely isolated system, can there be such a thing as a varying potential? Maybe not. But the point is that I want to know the behavior of the particle, not of the whole system. Like the experimenter has a particle, they put it in some potential and they want to know what it will do. They don't necessarily want to know whether a rat will appear under a chair because they did that. Okay, so energy can be transferred to the lab, but we don't want to focus on it because we want to know what the particle does. So of course you can put the whole thing in a box and isolate it, and then energy cannot enter or leave ideally. But that's really not what we do normally. Yeah, okay. So good, with all that, we have two equations and now we have to worry about what to do with them. And the first question that came up, and in fact Schrödinger did not have an answer to it right away, is the interpretation. So remember, again, every time we are stuck with some question, we should ask the classical question. and then try to transport it to the matter wave problem. This is why we spent time last week studying classical waves, because a lot of things are known there. Okay. So classically, alpha of x and t is a wave, and it's really the amplitude of the wave, and alpha of x and t mod squared is the intensity. Now in the case of waves, there are situations where you can directly observe the amplitude, but if you're only looking at the energy, you will observe the intensity. We had this discussion last week that intensity is proportional to the energy deposited by a wave. Okay, but this is fine, this is settled. What can we say about psi of x and t and psi of x and t squared? So after some years of thinking on this by various different physicists, one proposal which came out, which goes by the name of Copenhagen interpretation or probabilistic interpretation, is that first we interpret psi of x and t mod squared, and we say that it is the probability density for the particle to be at the point x at the time t. Now this is new, and it's not an obvious, doesn't have an obvious counterpart in classical waves, because we want the interpretation of the wave function for a particle, and always the particle you can keep in mind is an electron, because an electron is easy to produce, relatively easy to study, and it can be moved at non-relativistic speeds, so all the things we are doing should apply to the electron. Okay, and the claim here, of course, then they'll apply to everything, including even big objects like you and me. But to start with, the statement is that this is the probability density for the particle to be at x at time t. So first let's make the statement sharper, and then let's see what it implies. So to be precise, it means that psi, okay, first of all, I should have said proportional to. And why did I say that? If you remember, both the time independent and time dependent Schrödinger equations were homogeneous. That means psi appearing on the left, psi appears on the right. There are no factors of psi squared or any higher powers of psi. So if I multiply psi by 2 or 10 or pi or million or minus 1 or I, it still solves the same equation. So I cannot determine psi exactly from the equation. I can only determine it up to a factor, constant factor. So at best I can say that psi squared is proportional to something, not equal to something. Okay, so therefore, first of all, what does it mean to have, what is the probability density? We know what's a probability, but remember we are asking whether the particle is exactly at a point x. But we really cannot measure anything to be exactly at a point x. There is always some small error or some small variation in x. So the more precise statement is that this is the, again, proportional to the probability density to be in the small box around x of volume d3x. So I just take my point x, and I make a little box, and the volume of this is d3x. It's infinitesimal in the sense of calculus, and this is supposed to be proportional to the probability density. for the particle to be in such a box. Okay. Now, as I said, let's take this for granted right now and try to understand what it tells us. First thing you should realize is that if we do experiments with double slit type of experiments that we started this course with, then we found that for anything that we shoot at the double slit, whether it's a particle like an electron or a light wave, there's a probability it seems to behave as if it's going through both slits and interfering with itself. And probability is quite a satisfactory thing because it basically says that therefore the electron, when you shoot it at a double slit, has a probability to go through this slit and a probability to go through that one. Okay? That does not mean the electron divides into half an electron going here and half going there. And that's important because nobody has ever experimentally seen half an electron or any fraction of an electron. It is the easiest thing to detect because it would have a fraction of the electron's charge. And you don't see particles with a fraction of the electron's charge, in vacuum at least. Okay, so probability has certain satisfying features. But first, for this to be a probability density, it's important that it should be normalized. So total probability of particle being somewhere would be the integral d3x psi of x and t mod square, right? We just integrate over all space. So obviously this should be 1. But as I told you, from the equation, there's no guarantee that it is 1. You might solve the equation and I might solve the equation, and our psi solutions might differ by a factor of 10. In that case, this will differ by a factor of 100. So what we do is, we say that this is some n, and then we replace psi, whatever we calculated, by psi upon square root of n. Now those of you who are purists in maths will say, well, n is of course a real number because mod psi squared is a real number, but square root of n could, for example, have a plus or minus sign. Actually, we don't care much because any n which satisfies that, find this normalized one, integrates, its square integrates to 1, that's good enough for us.
So you should multiply by that.
No. We replace it by this in the sense that we normalize. Okay, so let's
Then that
understand
n
what
will
we
come
are
on
saying.
the R.
This side leads to the wave function. So the wave function, after we solve this, the correct wave function, therefore, which has a probability interpretation, is this one.
Understood.
And we say that it's a normalized wave function. And it's 1 second to see that if I put this on this side, I'll necessarily get 1. Because this square will integrate to n, this will also square and it will give me n, the two will cancel. And so then it actually has the probability interpretation. So one thing to always remember, any old wave function that you find by solving an equation cannot be assigned the probability interpretation that its mod square is a probability density. Only after you normalize it, then it can be assigned that interpretation. And this is good because it means that different people who solve the equation up to factors, after they do this, they'll all have the same solution. And so if anybody gives you, including me, including in an exam or a quiz, by the way, the quiz is this coming Friday, details will be sent soon. Anybody asks you to do something with a wave function, if we have forgotten to normalize it, then it's your job to normalize it. Or we might purposely not normalize it, then it's your job to normalize it. It's very important. Because otherwise probability doesn't work at all. Good. Okay. Now there's a small comment. I don't want to spend a lot of time on philosophical questions, but it is, yes please. Which one? Sorry. Thank you. Wonderful. I do make these mistakes. It is actual probability because I have actually multiplied it by the volume. Thank you. That's exactly what density is without that, and probability is with that. Yes.
This is for 3D wave.
Yes, this is 3D.
So
This-
for 2D thing, you should write it like D square.
Yes. Yeah, you can do this in 2D, 1D, 3D, and actually all are relevant. Space is three-dimensional as far as we know, but you might do an experiment on a planar material, then it's 2D. You might do an experiment on a wire, then it's 1D, and all such problems are interesting, and all such problems are addressed in laboratories, in actual laboratories, so they are all physical. Yes, there was another, yes.
Just the wave function without normalization doesn't have any physical meaning.
Well, it has the physical meaning that after I normalize it, it's a probability density. So it's only the normalization. So yeah, so what you can think is there's a family of wave functions, which is all the same function times any constant that you can think of. But any constant in general will be some complex number. So up to division by a number, it is actually, in fact, yeah. So actually we should write, yeah. So this is real, yeah, exactly what I just said. So you can think that one wave function by itself that I find by solving Schrödinger's equation is part of a family of solutions which are all the same function, just that they have 2 or 10 or pi or million or anything in front, any complex number, even I. They are all the same wave function. Okay, so after you normalize, then they really all become the same function also. So physical meaning is that it's the wave function, a probability density after normalizing. Yes.
So if you probability
Yes.
psi square and the qs, then why you are saying that it could be negative? Because
No, psi squared cannot be negative, but psi can be negative. That is important. I said psi can, it is psi that we normalize. We divide psi by something. We are not obliged to take a positive square root here. In fact, we can have any phase. We multiply psi by any phase, its mod square will not change. And it's always normalized, whatever phase I multiply
so
by.
n is always going to be a positive number.
Oh, n is guaranteed to be positive real number because mod psi squared is a positive real number. Mod of anything is a positive real number. I square it, then I integrate it. There are only two possibilities. Either this integral diverges, in which case I can't normalize it, or it converges to the number n and then I can normalize it. But if it converges, it certainly converges to a real positive number. There is no other option. Not only that, this integral will be 0 only if psi itself is everywhere 0, and that's literally the least interesting wave function we can imagine. Okay? Good. Okay, so now the point of philosophy I want to very briefly touch on is, people ask the question that people asked at that time, does this mean that nature is probabilistic? Because now we cannot know where the electron is with certainty. We can only know the probability of finding it somewhere or somewhere else. Okay, this was a whole storm of debate, and it led to Einstein saying things like God does not play dice and so on. I suppose you know some of these things from this reading. Now, the only point I want to make is that the wave function, nobody is debating that the wave function of an electron can be determined as a precise function, not the function itself is precise. Okay? What is imprecise is probability for finding a particle somewhere, probability for what is its position, what is its velocity, what is its momentum, what is its energy, those are all probabilities. But those things in classical physics were believed to be predictable quantities because they are essentially classical concepts. The concept of energy, momentum, position are all classical concepts built from macroscopic experience. In the microscopic domain where quantum physics is true and classical physics is not true, we simply give up the idea that position, momentum and so on are the basic concepts. They are no longer the basic concepts. They are some effective concepts which we can calculate only on average. But psi We don't give up psi. Psi is the wave function and it's an actual predictable or calculable thing. Okay, so in this sense, it's not probabilistic in that we don't just say that, well, there's a chance the particle could be anywhere, so it just could be anywhere and there's nothing more I can say. No, you can exactly say with what probability it is here, there, somewhere else, and that ability to predict means that quantum mechanics is a predictive theory. So that's as much philosophy as I want to get into. Now, immediate consequence. So we are going to look at consequences of these. If you want to look at alternate interpretations of psi squared, you can read about them. But you will see that eventually the community basically found that this probabilistic explanation works extremely well. So I don't want to again spend time going down the other avenues, but it is not obvious to people and people resisted it at that time. But a century later, this is clearly the correct answer, and it is part of the postulates of quantum mechanics. Okay, now let's recall that for a classical wave, there were two basic concepts, x and p, x and k, and there's an uncertainty in both measured by the standard deviation, and we had this relation. I didn't give you a rigorous proof of this bound, but I showed you an example where this is exactly half and you can calculate it. I also showed you how to estimate that it's roughly half or one in any case, just from pictures, for those who are interested. Now, since P is equal to h bar k, this immediately implies that delta x, delta P is greater than or equal to h bar by 2. And this is what is known as Heisenberg's uncertainty principle. So, actually, there is no big surprise that such a principle is true for waves. But when people saw this in classical wave theory, they were like, okay, well, a wave is a wavy thing, it's a fuzzy thing, so x has to have some uncertainty, k has to have some uncertainty. I can never localize a wave to be absolutely point-like. I can only put some kind of peaked function over the wave and try to make the packet very small. So delta x will be there, and this is the wave vector. To get a wave, I have to average over wave vectors, so there will be some spread in wave vectors, and very good. The product is has a mid-lower bound. Fine. Now with this equation, suddenly the words changed. Equation is essentially the same as that. Why did the words change? Because people said, look, this is a particle of position x, and that particle has momentum p, and you are telling me that I can't measure both of them arbitrarily well. Now, of course, no experiment can measure anything arbitrarily well, but in principle it can. That means if you have an experiment that has 0.01% error, you can always work harder and bring the error down. This is saying whatever work you do, you can't bring the error of both things down below this product, below this limit. So it's very baffling when you think that it applies to particles. But again, if you keep in your mind that these particles were never particles, they are secretly matter waves behaving as particles, then of course this is what you expect. So it's confusing when you insist on the rigorous particle picture, but that's a macroscopic concept which we developed over centuries of classical physics. Is that clear? Any questions on this? Okay, now this is a 1D version of Heisenberg's principle. It's very important to ask what's the 3D version, and for that what we'll write is delta xi, delta pj is greater than or equal to h bar upon 2 delta ij. This is the Kronecker delta, which is 1 when I is equal to j and 0 1 second otherwise. So this means that I goes from 1, 2 and 3. This is just the x, y and z coordinates, and pj are the px, py and pz momenta, components of the momentum. So this set says that there is no uncertainty between the x position and the y momentum. There's only uncertainty between x position and x momentum, y position and y momentum, and so on. That's very important. Yeah, there was a question. Yes.
Then can we not have a particle at rest?
Not have a particle at rest, exactly at rest, no, because if it's exactly at rest, then P will be exactly 0, and then its uncertainty in its position will be infinite. So it's at rest formally, but it could be on the moon at rest.
So, but
Yes.
doesn't this violate thermodynamic principle that at absolute zero everything should be at rest?
Yeah, in a sense you might say it does. We'll come to that. Thermodynamics was formulated earlier and has to be revisited. So the correct statement is that at zero temperature there is still systems, confined systems still have an energy called 0 point energy. And you might have already calculated it for all I know in some system. If not, we'll be calculating it in many systems. So the zero temperature behavior of a system is very quantum. And actually you must have realized that from the fact, it was a question in this quiz that I gave you on Friday, that the Planck radiation law basically says that at zero, it basically says you can't treat light as a wave at zero temperature. You have to treat it as a particle. Okay? That's where the wave interpretation breaks down in a big way. So zero temperature is very exciting, and by the way, you might know that ICER has several labs which are low temperature physics labs, and we have a helium plant. And why do we have all these things? Because those people are investigating quantum physics, and their best chance of seeing quantum physics is at very low temperature. That's why people use helium in the first place. People who don't care about quantum phenomena don't need helium and don't need low temperatures in general. Maybe for some other reason, but usually low temperature physics is an immediate giveaway that we are talking about quantum physics. Okay, so uncertainty principle was very simple and we've done it, and that's all we have to say right now. The only thing is we'll need to start calculating things soon, but before we calculate things, there's a small interlude. It will take me about 7-8 minutes, and if I don't finish, you'll read about it. And here we are going to talk about orders of magnitude, because I promised right in the beginning of this course that there was something called macroscopic and something called microscopic, and we don't exactly know what's the difference. But now we can ask nice questions with this principle and Schrödinger equation and other things in our hands. We can ask questions like, what is the uncertainty in the position and momentum of a normal dust particle? Or if you like, a normal motorbike. That's really very big. So we start with dust particle. Turns out that's also quite big. And then we'll ask what is the uncertainty in position and momentum of a normal electron. And we'll see that the difference between dust and electron is a lot. For this purpose, by the way, dust is, well, you should probably think of it as a cube, but I'll think of it as a set of 10 to, I think it's 10, yeah. It's about 10 to the 4 atoms. Okay? So 10 to the 4 this way and that way. You think of it as a packed collection of that many atoms. Okay? So it's a lot of atoms. It's 10 to some power of atoms. It's not just a few. Electron, on the other hand, is smaller than an atom, so a lot of difference. Now, let's start with measurements. Measurements on size. One can talk a lot about how these things are measured, but the estimates are that the size of dust is about 1 micron, which is 10 to the minus 6 meters. The size of an atom is one of the order of 1 angstrom. Excuse me? What?
Is that gamma?
R. R, the radius, if you can think of this as a sphere, probably better. Okay, this is 10 to the minus 10 meters, and R of an electron is of order 1 Fermi, and this is 10 to the minus 15 meters. And see the quite a big sweep of orders of magnitude. Dust is already something that you might say until the 19th or 20th century experiments would struggle to work with. Then came experiments that could look at atoms or their behavior, that's atomic physics. And then came experiments that could look at electrons, and that's particle physics. So there are key distance scales. Okay. Now, experiments can also tell us the masses of objects, and let's write down some masses that we know. I'll keep that equation there. So the mass of the neutron and proton, for this discussion, they are basically equal, and they are 10 to the minus 27 kilos. The mass of the electron is 1,000 times smaller, so it's 10 to the minus 30 kilos.
31.
Yeah, it doesn't matter. 1 or 2 orders of magnitude won't make any difference. The mass of dust, or 10 to the minus 13 to 10 to the minus 14. Okay. So I know all of you are very good at calculating things, but in this discussion, learn how to estimate things rather than calculate things. For this, we are trying to understand basic questions like, what happens if the uncertainty of a particle's position is like 1/1000th of a percent of the size of the particle? That means its location is 1/1000th of a percent uncertain. How much will it bother us in a real life situation? On the other hand, what will happen if I have a particle of some size and the uncertainty in its position is 1,000 times that size? How much will that bother us? You see the difference in these two situations. One, we don't have to care. The other, we have to care extremely, because anything we do forgetting that will be complete nonsense. If the particle's position is 1,000 times more uncertain than its size, then we could be in a nonsensical situation. So this is what we are trying to probe. Okay. Good. Okay. Now let's look at a de Broglie wavelength for a particle moving slowly. So lambda is h by p. So from this, from lambda we can find p, or in some cases we may know p directly, and from p equals mv. Remember, now we are only talking of non-relativistic situations. So we know the mass, we can find v. Or conversely, if we know the velocity, we can find its momentum and its wavelength. So let's consider v dust of the order 10 to the minus 3 meters per second. It's sort of slow drifting dust, 1 millimeter every second. Still visible, like if you watch it for a few seconds, it will drift 1 centimeter, you can certainly see it. Okay, then P of dust is m dust times v dust, so this is 10 to the minus 16 joule seconds per meter. All these calculations, they're trivial calculations, they are in the notes, you'll get the notes. So don't struggle to follow everything. But I've simply multiplied the velocity with the mass which is there, and I got this. Okay, so what's the wavelength of dust? According to this hypothesis, dust is also a wave, and it's a wave with some wavelength. And the wavelength of it will be 10 to the minus 33, which is a rough value of h, divided by 10 to the minus 16, which is this, all in MKS units. And the answer comes out to be 10 to the minus 17 meters. So the de Broglie wavelength of dust is 10 to the minus 17 meters, extremely tiny. Now, let's try to do the same calculation for an electron at a reasonable temperature, something like room temperature. and then I'll stop once you see the big difference between these two cases. So, for the electron, I'll assume it's free, but it's in a fixed temperature. So its energy is of order Boltzmann constant times the temperature. We'll take the temperature to be room temperature, and Boltzmann's constant is 10 to the minus 23 joules per degree times 300 degrees, joules per Kelvin if you like, and then 300 Kelvin. And so we roughly get 10 to the minus 20 joules. And from this we can find the, okay, what?
Momentum we can.
Yeah, from this we find the momentum. So this can be electron or neutron or anything, any elementary particle. Let's start with the neutron. So the neutron, we find from this that it is, momentum is 10 to the minus 23 joule seconds per meter. And therefore its de Broglie wavelength, which is this. So this time I didn't start with the velocity, I estimated its momentum from the temperature, and lambda of the neutron then comes out to be 10 to the minus 10 meters, which is 1 angstrom. Okay, now that is much bigger than the neutron itself. Okay, I didn't probably write the size of the neutron, did I? I wrote R dust, R atom, and R nucleus. R nucleus you can take to be comparable to the size of the neutron, because a nucleus has a few dozen neutrons. So a dozen is nothing for us. So size R of the neutron is 10 to the minus 15 meters. So now notice that the wavelength is 100,000, yes.
10 to minus 15 was of electron.
No, was of nuclear. Sorry, 10 to, sorry, excuse me. 10 to the minus 10.
10.
Yes, sorry. My mistake. That is true. So, yeah. So this is the same as the size of an atom.
100% error.
100%, yes. So they are comparable, while in dust it was many factors smaller. So the wavelength, you can also translate this into uncertainties. Now I might actually, after this lecture, rewrite my notes a little bit to express all this in language of uncertainties. But the basic bottom line is, dust, we don't have to worry about quantum effects too much. And neutrons, we start having to worry. And electrons, which are 1,000 times smaller, our worries will increase. So we see now that the microscopic domain is relevant for electrons or neutrons at room temperature, but it will also possibly be relevant for other things at much lower temperatures. So had we decreased the velocity of dust from 10 to the minus 3 meters to something very, very small, then again we would have found that its uncertainty or its wavelength is too large compared to its size. So this is important because estimating the size of a quantum effect can often be more important than calculating it. Calculating it, of course, is the final thing. You calculate, compare with experiment, check your errors, go to decimal places. But if your estimate, if you can't estimate, then calculating might not be much use. The first thing is always to try and estimate. And you'll see repeatedly in whatever I do, and probably also what Arka will do in the second half of the course, that we'll say things like, well, a particle is confined in a box, so the uncertainty in its momentum will be 1 over the size of the box, h bar over the size of the box. These are the typical statements we make. And some of them, I don't know if you know this historical fact, people for a long time thought there might be electrons inside an atom. Do you know this problem? Okay.
In an atom.
Inside a nucleus, sorry, not inside an atom. They are inside an atom, but they might be inside the nucleus. So the idea is, nucleus now we say is made of protons and neutrons, but what if it was only protons and electrons? We could manage to get everything right, atomic weight, atomic number, by just replacing every neutron by a proton and an electron, because together the mass is almost the same as the neutron mass, and the charges are cancelled, so it's like a neutron. Problem is, uncertainty principle completely contradicts that possibility, because the nucleus is inside 10 to the minus 10 meters, as we just saw, and you cannot confine an electron into that. Just the same calculation. Electron will not agree to be confined into that. So therefore, it's just not possible for the electron to sit in a nucleus. You can look this up. It's an application of uncertainty principle, and by the way, it's also a very common PhD admissions question in interviews. So it might be useful to some of you. I'll stop here.
Thank you, sir. So what particles